All right, hey everyone. Hope everyone's having a good Monday here. We're back with another audio programmer stream here. And yeah, today we're going to be talking about circuit model customization. And so to kind of give you a sense of what I mean by that, basically we have some circuit model in our plugin and we want to give the user access to as many parameters as we can that are relevant to that circuit. So the kind of place that I'm going to be doing this today is in the BYOD plugin that we've talked about before. And I'll give you a little example of what I've been doing in BYOD to kind of get this sort of thing working. So this is a debug build of BYOD from the other day. And I think the first thing I did this with was the tube screamer. So this is a circuit model of the drive stage from the tube screamer pedals, not the whole pedals, just the drive stage. And basically I added this way that you can view the circuit netlist. So this is the actual circuit schematic, and then over here is kind of a netlist of components. I don't know if I maybe want to change the some of the naming here, since this isn't just a netlist view anymore. It's also a netlist and the whole schematic. So yeah, maybe I want to change the name there, but the idea is that we can actually edit the component values directly. So we can't edit all the component values because the gain is kind of controlled by this R drive. The R drive resistor here is determined by the value of the gain parameter here. So at the moment, we don't have a way to edit that resistor, but all of the other kind of basic components, all the other resistors and capacitors, we can edit no problem. And yeah, just go ahead and change the value to whatever we want. And yeah, let's make sure that this is still working. It was working the other day, but I've changed some things since then, so who knows. Right, so this is not really a good test of anything signal processing related, because this is a nonlinear processor, and the EQ curve analyzer is really only meant to analyze linear processes, but it's still just kind of a good proof of concept that changing component values here will affect what the sound of the algorithm is doing. So for R4 here, this is this resistor kind of going from the feedback process to ground. So let's see if we make that smaller resistor. Yeah, so you can see that if we make that resistor smaller, we get kind of more of a scoop here in the middle frequencies. Again, not a particularly accurate frequency response, since this is a nonlinear process here, but yeah, so we can change the resistor value and see the corresponding change in kind of what the rough frequency response looks like. Let's try a capacitor here. So we have this C2 input capacitor. It's kind of a DC blocking capacitor. What if we make it smaller? Interesting. Oh, wait. Actually, that's not a DC blocking capacitor, I don't think. Yeah, I don't remember exactly how that works, but anyway, so yeah, if we make that smaller, then it seems like we get more of a kind of a cut here, kind of across these frequencies. If we make it bigger, okay, yeah, I guess it is kind of a low cut sort of thing. So if you make that bigger, we're moving the low cut frequency closer to 0. And if we make it, yeah, or sorry, if you make it smaller, yeah, that's right. If we make it a bigger capacitor, we move the low cut frequency closer to 0. If we make it a smaller capacitor, we move the low cut frequency to a higher number. But yeah, that's kind of cool. So that's the idea here with this circuit customization, is that we can directly choose different component values in our circuit. aside from the component values that are already determined by some of the other parameters that the user already has access to. So yeah, I've done this for a few things in BYOD now. The most recent one is the, where to go, basement tone. So here's the netlist for the basement tone. And yeah, we can kind of see the circuit overall, and we can change some of the component values. Probably won't look like anything unless we also give it some shape. Oh, wrong way. Yeah. There we go. And then maybe we'll make this, I don't know, 1 picofarad instead of what it was before. What was it, 200 or something? Yeah. What if we make it even bigger? Or sorry, even, wait, yeah, bigger. 900p. Okay. What if we do something like that? Okay. Yeah, so we can get some interesting results from messing with the circuit schematic like this. And yeah, that's kind of the idea here, is that part of the whole reason that we're doing circuit modeling in this plugin in the first place is to give the user access to, you know, the circuit model itself through the parameters. And so now we're kind of extending that to give the user access to even more of the things underlying the actual sound. So yeah, this is a cool thing that I'm happy to have in the plugin. And so now we've just got to do it for some more of the processors here. So yeah, a number of these aren't really circuit modeled or are doing different things that I'm not sure would play super nicely with this kind of customization. But yeah, I'm going to try to do it for as many of the processors as I can. So I'm excited to play around with this a bit more. So let's go back to nothing here. I think the first circuit I was going to do is the Baxandall EQ circuit that I've been working on. And let's see, I've got this link here. Is it trying to go? Okay. I have a copy of this paper somewhere, but I don't remember exactly where. But yeah, it might be a little bit tricky for me to get the paper through IEEE, given that I don't currently have an IEEE account. So this is a Kurt Warner paper on, well, let's just search Baxandall EQ. Might find it. Here we go, modeling circuits with arbitrary topologies. There we go, we can download the paper. I might already have it downloaded, or maybe not. Cool. And yeah, let's see what we got here. Yeah, this is kind of a cool paper if folks are interested in this kind of thing. But the idea is that they're taking the wave digital filter modeling paradigm and kind of going into modeling circuits with topologies that cannot strictly be broken down into series and parallel connections. And I think this was actually the first paper to kind of really go into that, direction, at least in the way that Kurt was doing it. And still is doing it. But yeah, it's a super cool paper if you're interested in this kind of thing. What was the other circuit that they did? So they did the Baxandall EQ, and then they did a frequency booster, which I think is kind of like a range master. Figure 6A. Figure 6A. Oh, okay, no, it's just like a linear filter. I guess this is from the Anderton book. I don't remember this one exactly. But yeah, I guess it like kind of boosts has like a bell filter boost kind of thing. Interesting. Anyway, yeah, I don't have a model of that circuit in BYOD. Maybe we can add that eventually. But what we do have is this Baxandall EQ. And so I'm just going to go through my implementation and make sure that I'm using the same names and whatnot as Kurt's paper is, so we don't run into confusion later on if things don't match quite right. Let's do that. Cool. All right. So so we've got Vin, that's our input voltage source. We've got Vin here. Where's Vin? Okay, Vin is the final port in the R-type adapter, and then we've got CA. Let's make that big. There we go. We've got CA as the series capacitor connected to that. Cool, cool. Let's see, what do we have next? We have treble, RD, and CD. So PT plus RD and CD are in this next sort of branch here. Interesting. Why is RD there? I guess it's in parallel with PT, right? Yeah, okay, that's a little bit subtle. Next, port B, we've got PT minus, resistor E. PT minus, resistor E, those are in parallel. And then we've got RL and CD also in parallel, makes sense. And we can actually combine those. I've been working recently on figuring out ways to combine WDF elements, so we can definitely do that. Might want to combine those as well, since they're just parallel resistors. Yeah, I'll think about that. Okay, we've got RC, that's probably on its own. Yep. We've got RB, PB minus CC. PB minus CC, res B, cool, cool. Then PB plus CB and RA. Cool, yeah, so it looks like we've got all of the circuit components necessary in our model. And we've got everything, seems to have the same names. There's no naming confusions. That can be a challenge when going between circuit schematic and some code, making sure that everything has the same name. But it looks like we're in the clear here, so that's a good sign. So, yeah, I think the first thing I'm going to do here is actually make the circuit schematic. So I probably could just copy this schematic from Kurt's paper, but that would probably be a bit of a copyright issue. I don't know exactly what the rules are behind that. But the bigger issue is that I've kind of got this style that I've been using for all the other ones. It would be cool to keep everything within the same style. So yeah, I think I'll do that. So I've been using this little circuit diagram tool here, and we'll call this Baxandall EQ. And yeah, so first we need a voltage source, so we can create that voltage source, and that's going to connect to ground. And I've been spending a lot of time doing this lately, so sorry if I'm going a little bit quick. But yeah, I don't know, maybe a little bit tired of spending a ton of time in the circuit schematic editor, but it's not so bad. This is a decent tool here. All right, so next we have CA, and we've got kind of this two-branch system going down. So let's see. I'm going to do it this way. So I'm going to have a wire coming out from there, and then capacitor. It's this capacitor CA over here. All right, CA. Next, we can have RA going down, I guess. A. And now we kind of this weird network with C coming out and PV going down. Let's do PV first. So we've got a potentiometer here. We'll call this R base, since that corresponds directly to the parameter in the parameter in the plugin. Cool. Yeah, that'll be fine. And then yeah, and that kind of matches with the naming I've been doing in the other schematics as well. So yeah, let's see here. Next, we've got CB and CC coming out and then kind of connecting to that. So let's do that here. Capacitor maybe coming from there, and another one coming from there. So this is CB on top, and CC on the bottom. And then we can have these connect to each other and also to the third pin of the potentiometer. Easy enough. And I'll put a resistor here, which we'll label later. And then we've got RB going to ground. Cool. Easy enough. So let's move this around a little bit. So this is RB, and then we've got ground at the bottom of that. Cool. And then RC is our bridge capacitor, sorry, our bridge resistor here. So yeah, the way this circuit is more or less designed is that the left side here manages the bass frequency response, and then the right side here is going to manage the treble, the side that I haven't put in yet. So yeah, we can do a very similar thing here, actually. Just have this wire coming across here, and then we'll have these two resistors coming over this way. And so that'll be RD and RE. Alessandro says, BYOD is so cool. Thank you. Yeah. So I don't know if I'd mentioned this yet, but we're planning on doing a update for BYOD this summer. This is kind of the first, I don't know, maybe the first thing I've done talking about it. But yeah, this is one of the features that we're really excited about. And we're going to have a few more coming up, which, yeah, maybe I'll talk about those as well, or maybe maybe those will just be a surprise for when it gets released. We'll see. But yeah, we're very excited about BYOD and some of the stuff that we're going to do with it this summer. It'll be a lot of fun. Oh, I see. So RE is actually split across these two things here. Sorry, RL and CE are split across RE like that. So I'll do capacitor here and resistor there. And then I'll just have both of them go to ground. And then, yeah, hopefully these labels don't get in the way. That would be annoying. And then last but not least, we're going to have another capacitor going up there and a wire coming across. I think that's all of our circuit components. Now we can label them. So we've got CD and CE. CD and CE. And then this here is RL, which is our load resistor. What did they give for the value of the load resistor? They did 1 mega. Okay. And some of the other circuits, I haven't actually been giving the user the option to edit the load resistor, because for a lot of circuits, it doesn't really make a difference, but maybe we will here. We'll find out. Yeah, so this looks like our full schematic. Let's save it. Let me just double check it a couple times here, make sure that I'm not missing anything. Yeah, that looks about right. Cool, so let's download it and then we can add it to the plugin. So this will be backsymbol EQ schematic.svg. And then I have my CMake set up so that all the SVGs in that folder will automatically get pulled in. However, it also means I need to completely rebuild the plugin, which is going to be a little bit annoying here. So let's get that started while we wait for everything else to happen. But yeah, let's look at the implementation we did for the baseman. And maybe that'll, this is annoying. Is there a way to make this disappear? Hide video panel? No, don't hide that. Hide floating meeting controls. Cool, there we go. That's handy. All right. Yeah, so this is basically what we want to do here, is to create this netlist circuit quantities thing. And for that, we'll need this include. And we can toss that in here. I've been switching to trying to have fewer relative include paths in my code here, so hopefully that'll be helpful as well. And then here, we can basically just copy this directly as well. Except here, we're going to need, let's see, backs and all EQ schematic. I could spell it. SVG. That looks about right. There we go. Cool. Yeah, and so then we would add all of the circuit components that we want the user to be able to edit. So, for example, this is how we would add a resistor. This is how we would add a capacitor, and so on. And so we can start doing that, but I'll give it a second here for the compiler to catch up. But yeah, so from here, we should be able to view the circuit schematic and view basically an empty net list that has no quantities in it, which makes sense because we haven't added any quantities. But yeah, while this is happening, maybe I'll show a little bit of what's going on behind the scenes here. So basically, we have this circuit quantity struct. And right now, the only circuit quantities we can have are resistors or capacitors. I might change that in the future. There's some like voltage sources that maybe would be cool to be able to edit, or maybe like some diode parameters. I don't think we have any inductors in BYOD, but if we did, we could add that too. And then we've got this setter function, which we can kind of come back to. But basically, it's this fixed size function that Juice has. Fixed size function is kind of cool. It's basically a similar thing as a STD function, but the idea is that because it has a fixed size, you can allocate it on the stack, you can move it around and do whatever you want with it without having to worry about memory allocations. So that's a pretty nice thing to have. Yeah, and they describe it pretty well in the comments here. So creating a fixed size function will never allocate, and deleting a fixed size function will also never allocate. And so that means you can use them in real-time context, which is nice. We also have a value. So this is like the base value of the quantity. And we have another atomic bool that will tell the DSP whether this needs an update or not. And then we've got another bit of data here. So we have a default value, min and max value, and a string for the name. And then we have a setter function. So this is the data that every circuit quantity needs to have for us to do what we need to do with it, including displaying it on the UI, updating stuff in the DSP, and so on. Conrad says the delegate implementation in include OS does the same thing as fixed size function. Interesting. Delegate. OS. Oh, okay, this is an Apple thing. Am I looking at the right thing from what you're expecting? Sorry, I might be looking completely in the wrong place here. Becoming the delegate. I feel like I'm not looking in the right place for what you were trying to tell me. Yeah, sorry. If you have more info about the delegate implementation, I'd be curious to see it. But yeah, I actually tried to implement my own fixed size function a little while ago, and what I ended up with was like 95% the same as the juice implementation, so I just stuck with that. But yeah, I'd be curious to know a little bit more about the include OS implementation that you're talking about here. Sounds kind of interesting. But anyway, our build has finished, so let's take a look at what we've got here. All right. So if we go to Baxandall EQ, we should now see a show netlist thing. And we don't see that yet. Maybe I just need to rebuild because I added these lines, and I think that was after I did the last build, but this should be a quick build here. I feel like the link time with BYOD takes too long. I think there's a way to improve that. But I don't know, everything takes a long time when I have Zoom running, so who knows? Anyway, cool. So we want the Baxandall EQ, and now we can see the netlist. Yeah, so there we go. So the schematic that we were just going through in the circuit diagram page is now here in the plugin. So that's kind of a quick and easy way to create a circuit schematic that you can visualize in your plugin. Not sure if anyone else needs that for any reason, but seems to work well for me. Yeah, I don't know, maybe there's some ways that I might want to style it differently to try to look cool, but I think I'm okay with how it is for now. Cool. So I think what I want to do next here is basically do some modifications to the circuit itself, or sorry, to the WDF model itself, just to kind of simplify things especially with some of the newer ways I've been doing things. But for that to work, I need to basically have like a kind of a test case so that I can compare things. So what I'm doing here is on the audio 2 track, I'm just going to have a second instance of the plugin and the EQ curve analyzer. What did I do? Okay. And I'm going to use the VST3 version so that these these two versions don't conflict with each other. But basically, what I'm going to want to do is have a reference version of the Baxandall EQ module. Oh, wrong one. Yeah, the Baxandall EQ processor here. So that way I can compare. I can compare with the change. I can compare the changes I'm making against the existing version and make sure that I'm not breaking anything. So, for example, if I bring the bass knob all the way up, that should be the same on both. Yeah, on both of the two plugins here. So the gray line is the VST3, which is like the old version, and then the green line is the clap build, which is the one I'm making changes to. So that one will be kind of up to date with whatever changes I'm making, which will be nice. Cool. So first things first. Yeah, so I guess first we've got these two resistors here, PT plus and ResD. And these are just two resistors in parallel. So there's a easy way to combine resistors in parallel. Also, I'm just going to make everything public, which I'll explain that in a couple of minutes. But let's see here. So yeah, so what I want to do is I want to have, well, let me think about this. So I want to have a method for parallel resistors. Float R1, float R2, and the combined resistance of two parallel resistors is going to be R1 times R2 over R1 plus R2. And the reason I have that memorized is because I used to be an electrical engineer, and that was like required reading for us. But anyway, I'll make this a one-liner here. So it's static, inline, and whatever. And we'll make it, except two, I guess. I don't know, all the things. But yeah, basically what we want is when we set, basically I want to combine these two resistors. So I want to have a new resistor that is, this will be PT plus in parallel with ResD. And so this should be, the value should be parallel resistors with the value of the first one and the value of the second one. Oh, that won't be semicolon there. Yeah, so that's basically what we want here, so that we don't need to have these two parallel resistors. Problem is that, well, there's actually a few problems, but the biggest problem is that when we set the value, because PT plus is connected to this parameter, we need to have some extra logic happening here to make that work correctly. So what I'm going to do is I'm going to do float ResD equals 10K. And then here, I'll do this is now equal to parallel resistors with that as one of the values and the other one being ResD. Cool, so we've just combined those two. And for now, let's just pop these both into the series adapter here and make sure that we didn't break anything. So the idea here is that I'm just trying to condense our circuit model into partly into less code, but also into less stuff that the compiler has to optimize through. And basically, I've found through some just empirical noodling that seems to improve some of the compiler generated code and lead to a faster result, which is kind of nice. So yeah, that's what we're doing here. So let's make sure that didn't break anything. So this is the in progress version of BYOD. And it seems to be behaving the same as the other version. Oh, this didn't save very well, did it? That's too bad. All right, Baxandall EQ. And this should be on group 2, which we can underlay. And yeah, so it seems like these are exactly equivalent. So if we put them at the same parameter value, they overlap perfectly. That's good enough for me. So next, we can actually combine the resistor and capacitor here into this resistor capacitor series element. And I'll just keep this one named S4, just because. Actually, I'm not going to do that. I'm going to name it PT plus resd CD, just so that all of the components that are included in it get their place in the name, and that'll make it easier for me to find later. Cool. So that means I need to edit some things later down here, because otherwise we're going to have some missing identifiers. Cool. And then here, I also need to change this so that it has both of those. So it has the correct name now. And yeah, so now we should be able to build. Actually, no, we're missing this one. Oops. Yeah, so now we can build and test again and just make sure again that I didn't break anything important. Hopefully I didn't, but I guess we'll find out. Nope, I did. Okay, yeah, we can just swap that in as well. Cool. So yeah, that's a much simpler port A than we had before. Previously we had, actually we can just ask Git what we had before, because I won't remember it. Yeah, so previously we had 5 WDF elements, and we've condensed that down to 1. So that's kind of nice, and it should help our implementation be a bit faster here. I'm not going to do a rigorous benchmark here, but even just comparing the VST and the clap builds, I imagine we'll see some difference. So this is VST, this is clap. Well, we'll see a difference in the wrong way, because this is a debug build, but whatever. Yeah, and let's just make sure that we're still getting the correct result. Sure looks okay to me. Nice. The reason I'm only testing the treble knob right now is because the bass knob is completely separate from the stuff that I'm working with there. Or sorry, from the bits of code that I'm editing. All right, so now we can simplify port B a little bit as well. I'm not sure we can go quite as deep with this one, but the very first couple steps here should be the same. We've got a resistor, 2 resistors in parallel, and then a capacitor in series with those resistors. So let's just copy paste here. So this is PT minus, this is res E, and this is CE. Well, is CE really in series with those? RL. I feel like something is off here. Maybe I don't want to ask too many questions because it works. So here's CE. Those two are in parallel. Are they in parallel? So this, we have a node here, right? Yeah, so those two are in parallel, RT minus and RE. It seems like they would be in series with the parallel combination. No, because RE is in between. Sorry, I'm getting all caught in the weeds here. No, okay, that makes sense. Yeah, that's totally fine. Yeah, those are in series with CE, and then RL is, I guess, in parallel. Yeah, because that's going to ground. And that path is going to ground as well. I think I've been through this before, and it kind of threw me for a loop that time too. But that's okay. So we've got float res E equals 1K. And so yeah, we can just do that kind of the same way. This is 64 instead of 6.4 for CE. And then we can get rid of a bunch of stuff there and finish simplifying like so. And yeah, then we also need to edit here. So we want to do that. And this should again be a couple of parallel resistors, this time with res E. And yeah, there we go. So yeah, let's make sure that that still works correctly. Port C, we can't really simplify at all because it's just a resistor. Port D, we could combine those resistors and or that resistor and capacitor. Port E, we could combine a resistor and a capacitor. And then port F, I don't think we can do anything at all, which is fine. Here's water. All right, let's give that a try. So this is clap. This is VST3. This is our EQ curve analyzer. And yeah, it looks like the treble control is still working about right. Cool, cool. Good to see. Hey, Ethan's here. Good to see you, man. Yeah, we're doing some WDFs today. This will be a fun time. Or at least I hope it'll be a fun time. It's fun for me. So yeah, here we want to have a resistor and capacitor in parallel. This will be PB minus and CC. And again, we can do our values here. So this will be PB times 0.5. Oops. Times 0.5. And this will be 220 E minus 9. And then we should be able to get rid of that. CC and PB minus. Cool. And then for PB plus, we can do basically the exact same thing. So this is PB plus, this is CB, and this is going to be 22 E minus 9. set our resistance value, prepare our capacitor, and yeah, all right, I think this should be our last bit of circuit simplification. And then we can get back to the customization. That was a parallel connection, right? Make sure I got that right. So that was parallel. And that one was also parallel. Cool. Cool. So once again, we just want to make sure that this matches with what we had from the previous version of the plugin. So you can compare against an old build here. So let's see. That's the old version. Here's the new version. There we go. Yeah, cool. Looks good to me. Nice. Cool. So yeah, now we can get back to the fun stuff of getting our circuit customization working. So let's see. Yeah, so we're going to have a bunch of resistors and then a bunch of capacitors. So let's go through it here. So netlist circuit quantities, add resistor. This one will be, yeah, let's see. Let's do RA first, I guess. And RA is, what's the value of RA? The value of RA is 10 E3. So that's a 10K resistor. This is RA. And then let's see, we're going to want a lambda there. So the lambda, the job of the lambda is to actually set the value, like whenever the value changes, this will be called to set a new value here. So let's just copy this in for now, I guess. So the idea here is that we can use the quantity, capture this, and then set the actual model parameters. So we've got this WDF circuit thingy here. WDF circuit, this should be res A, set resistance value, and it's going to take the circuit quantity and load the value atomically and use that to set the resistance value. So the idea here, well, this is actually why we wanted to make all those variables public before, so that we can edit them here. I don't know, maybe some C++ experts would say it would be better to use a getter function there, but that would be a lot of getter functions for all of these circuit components. So I don't really feel like doing that. And then here, the idea is that we can actually set limits for what are the maximum and minimum values of the resistor. For now, I'm going to do 100 ohms and 2 mega ohms as the limits, but we can edit that later if it seems like there's going to be stability problems or the signal is going to become like way too quiet to hear or something like that. We can kind of do whatever we want with it. So yeah, next we've got res B. This is 1K by default. This is 1K. And yeah, I'll keep the same limits. We can mess with them later if we want. I'm going to go ahead and do res C as well, just to keep things interesting here. So let's do RC. This is also 10K, res C. And yeah, let's give it a try, see what comes out. Whew. All right. Cool, so now we can actually modify the circuit components directly and see what effect that has on the frequency response. So if we show the net list here, we can kind of pull these above each other. So yeah, let's see, RA, RB, and RC seems like they're all kind of around the base parameter control. So let's see, what if we change this to 1K? We kind of get a boost overall. Makes sense. 100 ohms. Okay, so if we make it too small, then we kind of get a boost in the treble frequencies as well. That's interesting. What if we make it really big? Interesting. So now we kind of got this dampened low frequency response. That's interesting. Set that back to the default. RB, I would imagine, works in kind of the opposite way. So if we do 100K, that becomes really big. If we do 100, we get this kind of big notch here. That's interesting. Yeah, that's super interesting. Huh. That's pretty cool. And then what about RC? I'm kind of curious what we'll get from RC, because RC is sort of the barrier between the bass circuit and the treble circuit. So maybe we'll lift both of them and see what happens with RC. Okay, so if we make it big, it kind of tilts everything towards a treble boost and a bass sort of dampening. That's interesting. So this is 100 ohms. That's 10K, which is the default, and then that's 1 mega. That's very interesting. Cool. Yeah, so that's kind of the idea here, is we can just make this user editable parameter if they want a funky frequency response like that, and they can get it. Cool. So next we want to do RD and RE. I'm going to throw RL in there as well, just to see what comes out of it, and then we can move on to the capacitors. So RD, RE, and RL. Just copy paste a few times. So this will be RD. What is the value for RD? Oh, so this is one of the ones that got subsumed by that parallel connection. So we can go ahead and do that here. So this will be 10K by default. And then here we can just do res D equals that value. And I'll do the same bounds for now. I don't really feel like changing them. And so what's going to happen is res D is going to get updated by this setter here. And then when we set the parameters in here, that's when that's when the internal WDF element resistance will get changed. So that's res D. Res E is 1K. We can do a similar thing. And then finally, RL. Where's RL? RL should be in port B. It's 1 mega by default, so 1E6. And here we'll just set RL. And I don't know, do we want to make the upper limit a bit bigger? We'll try that. And yeah, let's see what that gives us. Yeah, so I don't know who's actually going to use this circuit customizer in BYOD. I'll probably fiddle around with it a bit. But yeah, I don't know, maybe kind of a cool thing so that people can, first of all, just sort of see the demonstration that it is like a sort of a deep circuit model rather than like a snapshot model or something like that. And also, yeah, just to, have some fun, learn about circuits. I like learning about circuits, so I don't know, but maybe I'm a little biased by my love for circuits, but that's okay. Cool. So yeah, let's try dampening things here and see what we get. So RD should adjust the treble response. Maybe let's do something like that. I don't know. It's kind of interesting. Anyway, so RD will have this be K. Okay, so that'll boost things a bit. What if we do 100K? I'll kind of dampen it a bit. Let's make it really big. Doesn't do much. Really small, just boost it more. RE, maybe we'll do the opposite. Yeah, so if we do a big number, then it becomes really big. If we do a small number, it becomes really small. And then RL, I don't know if this will actually do anything. Okay, it kind of does. Yeah, it just makes everything really quiet. Okay, yeah, that could be a fun parameter for people. Yeah, and then after probably, I don't know, probably after that, you don't really get much more from it. So maybe I'll just cap it out at 2 mega or something. Cool. So now we're ready to move on to the capacitors. So yeah, let's take a look here. Starting with CA. Where is CA? Oh, CA is down here. This is 1 micro. So 1E minus 6 CA. CA dot set capacitance value. And we'll do maybe from 1 picofarad up to maybe 100 millifarads. I don't know, just to kind of spitballing some limits here. We'll have to test that out and see what that range actually gets us. And yeah, let's do a couple more just to see what they look like. So this will be CB and CC. So for CB, what do we got here? For CB, we've got 22 nano. That's CB. And so this will be E plus and CB. We'll do the same range, maybe. Yeah, probably fine. And then for CC, that's 220 nano. Oops, CC, there we go. Cool, let's give that a try. But yeah, so I guess this is kind of the fun part of doing this kind of programming work. I was able to get most of the hard stuff out earlier, which is all the stuff here. But yeah, now that it's now that's mostly taken care of, it's kind of fun. We can just kind of waltz through the setting up the diagram and figuring out the ranges for each component and just having some fun with it. And yeah, it's a good time. So let's see, show net list. So right now we've got CA, CB, and CC are the ones we're going to be dealing with. So CA, what if we make it 1 pico? Everything goes away. What if we bring it back? Okay, it comes back. What if we do some phase boosting? Okay, seems like, yeah, okay, seems like this is adjusting the low frequency response a bit. So yeah, maybe we don't want to let people go that far down. Maybe 100p or 1 nano is a good limit. Let's see. We'll do 100p. That's fine. Yeah. Ethan says, I'm prototyping inside BYOD all this week. Hadn't realized what the netlist thing was for yet. Now I know. Yeah, the netlist thing is super new. I just started working on it maybe a week or so ago. And yeah, I'm pretty pumped about it. It's a cool feature to have. And yeah, I think for people like us who are kind of circuit nerds, it's a fun thing to be able to mess around with. All right, so CB. What if we make that really small? Doesn't seem to do anything. What if we make it really big? Okay, it seems like it kind of adjusts this bump here. So maybe it matters more if we're trying to attenuate the bass. Yeah, there we go. So now if we do something small, we've got more attenuation. But yeah, it doesn't seem to be, well, it's like a good 12 dB boost or so. So yeah, it does make a big difference. That's kind of interesting. And then what about CC? Okay, yeah, so if we make this too large, then it kind of takes away all of our boost. Yeah, there we go. That's cool. Neat, yeah. All right, so now we've just got CD and CE remaining, and that will take care of the rest of our net list here. All right. So CD is 6.4 nano. CD 6.4. And CE is 64 nano. Oh, there we go. Here. Cool. Here we go. So yeah, now we're messing with things that are near connected to the treble potentiometer. So maybe it'll make more sense to hang out up there for a second. So if we make that small, yeah, that makes a big difference. And then we go big, it kind of flattens everything out up there. That's cool. Interesting. And then CE maybe does something kind of opposite. Yeah, kind of drops the low frequencies or brings them back up depending on how we have it set. Interesting. Yeah. That's pretty cool. Sweet. Yeah. So now yeah, lots more fun circuit tweaking folks can do if they're interested in doing that. And yeah, there we go. We've got our Baxendale netlist working. Cool. Let's see, what time are we at here? All right, we've been going for maybe an hour. Do we want to try doing one more? That's the question. Hmm. Let's see, let's get some water. So if we were to do another netlist view, what circuit would we do it for? Looking at my list here. Maybe the treble booster. Let's take a look at the treble booster. Maybe that one could go quick. Or maybe would. Well, I guess since Ethan's most responsive, maybe would you prefer if I go through kind of how the circuit quantity system is set up, or maybe we do another one? I guess it's up to you. Yeah, I'm happy to go through either. Treble booster is kind of interesting because that one's not a WDF. That one's not a WDF circuit model. That one's a just kind of a nodal analysis model. So maybe that would be interesting to look at for that reason, because all the ones I've done so far have been WDFs. So I'm not 100% sure how I would want to do it in the nodal analysis domain, especially since the treble booster has this funky thing we need to do where we flip the poles. Yeah, let's do the treble booster, see what happens. What I'm worried is that we may need to have this pole flipping be conditional. So we might need to figure out where the poles are and then decide if we need to flip them or not. That would be kind of annoying. So one of the things with the way I've been setting this up is that I want it to be basically, I want it to be set up so that if you're not using the netlist viewer, you don't pay for it in terms of CPU costs. So the CPU usage and the computations that are being done should be exactly the same as the previous version of the plugin if you're not using the netlist view. But if you do want to edit the circuit directly, then maybe there's a tiny bit of extra CPU, but if you're not using it, we really don't want any extra CPU usage or things like that to be happening. So here's our treble booster. So it's the tone control from the Centaur, as Ethan mentioned. So hopefully I named things the same. I don't remember. So yeah, here at the positive terminal of the op amp, we've got this, basically it's a virtual ground. In our case, we don't really care because it's just, for us, we could pretend it's ground because this is a linear circuit, so we don't really care. Treble booster circuit works well in the analog realm. If you adjust component values in view ID, you can blow it up. Yeah, yeah, that's the pole flipping thing. So yeah, let's see. We might need to be creative to figure out a good solution to that. I also wonder if I still have my. I had some Python scripts kind of showing why you need the pole flipping. Centaur. Man, I hope I kept those Python scripts. Subcircuits. Here we go. Yeah. I have pole zero plots. Yeah, okay, yeah. I didn't have the plots that I should have had. But basically you can kind of see here, this is why I print the roots. So you can see when they're you can see when the roots are in an unstable region. But yeah, we can think about how we want to do this. I don't know, maybe having an if statement there wouldn't be the end of the world, especially since if you're not using the netlist viewer, you'll always take the same path through the if statement, so the branch predictor will help you out, hopefully. Yeah, we can have some fun with this. So we've got kind of a simplified thing here as far as the actual circuit components, because we are kind of pre-computing these G values, which are like conductance, I guess. So we've got yeah, okay, so we've got R pot. We've got C. What is C? C should be a capacitor. Oh, here we go. Okay. So G1 and G4 are 1 over 100K. So those must be 100K and 100K. I don't remember which one's which, though. Man, I documented this all somewhere, but I don't remember exactly where. Our pot is 10K. That makes sense, yeah. So we've got the positive half and the negative half. We've got our 1.8 and 4.7, which are floating around somewhere here. 1.8 and 4.7. And then we've got C, which is the capacitor at 3.9. So so I think we can just go through and set this up directly. Problem is remembering which one is G1 and which one is G4. So I don't remember that off the top of my head. Maybe I rewrote some things somewhere and that could help us out. I think I did this actually. So let's see. Oh, no, don't do that. Ethan thinks R22 is G1. I'm inclined to agree. Sounds good to me. We'll do it. And if it seems wrong, we can change it. Although I guess how would we know that it's wrong? That's the tricky question. All right, so the first thing I'm going to do is make these just regular member variables, which is not ideal, but you know, whatever. And then let's see, this can no longer be const expr, fine. And then 1.8 and 4.7 we'll have to do just as regular resistance values rather than conductance values. So R21 is 1.8K. K, and then the other one is R23. So for now, we're guessing this is R22, and this one is R24. And we can correct that if it's wrong. Oh, whoops, I got that wrong. 4.7. Okay, that's right. Yeah, cool. So now we need to edit the coefficient calculators to actually use these values. So that's R21 and R23. I think that should work out right. Cool. And so that stuff might change CPU usage a tiny bit, but should be pretty minimal. And yeah, so let's just set up the netlist viewer, and then that's probably going to blow up, but you know what? It's fine. I mean, it's not fine, but I've got my track muted, so we'll blow up our speakers, and then we can fix it, and then it'll be fine. Let's see. So I guess for now, I'll just use the old schematic because I don't really feel like doing the new one right this second. Or sorry, the schematic from the basement tone, because I don't really feel like implementing the treble booster schematic right now. So let's see. We've got 100K for our let's go in order. R21 should be 1.8K. Here, okay, here we can do it like this. So equals that. And we'll put some limits on this, maybe 100 ohms up to 2 meg. And yeah, we may need to back off those limits a little bit if it seems like maybe things are going unstable, or maybe we need to deal with our pole flipping differently. We'll find out. So next we want our 22. This one is 100K. And we said that R22 corresponded to G1. We'll say G1 equals 1 over that. And then let's just copy both of these so we can do this. So 4.7 and R24. Yeah, all right, so this is G2 and this is R23. And then let's just go ahead and do the capacitor too, since we're here. Oh, oops, that's G4. Yeah, okay. All right, so capacitor is 3.9 times 10 to the minus 9. Capacitor. $3.9 and 10 to the minus 9. This is, they're calling it C14, so we can do that too. And we'll just do C equals self dot value. Yeah, so let's do that. Probably going to blow up, but we'll use that as a starting point. While that's building, let me see if I can figure out where these numbers came from. I might just need to go through the nodal analysis again. That'd be kind of annoying. I feel like I had it written down somewhere, and now I don't remember where. Did I go through it in the paper here? I think I did actually. Oh, here we go. Yeah, okay. So this is the Laplace domain. So 1 over R22, 1 over R21. Sorry, R24. 1 over R24. And this is in the S domain. Let's see if we can. Let's see if we can figure out what I was doing way back when I wrote this stuff. Okay, so B0 equals C times G1 plus G2. So G1 is that. C times G1 plus G2. And that's times S. So G1 should be 1 over R22. And that seems to line up well with what we've got in the second term here. Okay, yeah, so G1 is R22. So yeah, Ethan's right. Thanks, Ethan. You remembered what I did better than I remembered it. That's always nice. All right, let's see. what we've got here. So open things up. So yeah, I'm guessing this is going to go unstable. So we're going to keep this track muted. At the very least, we should not have any blowups. So let's see here. Treble booster net list. So this is the wrong schematic, but the correct net list. And we'll see what we get there shortly. So that's the max boost. What should we do first? Let's see. So R21, let's make R21 small and see what happens. Okay, that seems fine. And then what if we make it big? Okay, that seems fine too. So I bet we could just do whatever we want with R21 without any consequences. That's nice. R22. All right, that's this kind of series resistor for the op amp. Let's see what if we make this small. All right, that seems like a blow up. Okay, no, not a blow up, just something quiet. What if we do 10K, 1K? Oh, okay. So it just gets super, super loud. Okay, so maybe, so this makes everything really loud, but it doesn't seem to make it go unstable, because if it did, we'd get not a numbers and we wouldn't be able to get back to something that is stable. So yeah, maybe we just limit this one to like 5K or something. I don't know. Even that's kind of 10K is the default value. No, 100K is the default value. All right, let's limit R22 to 10K. Because for anything below 10K, seems like it just gets really big, but not unstable. Good to know. If we, so 100K is the default. If we go higher than that, what do we get? So we just see some drops in the low frequency. That's cool. All right, I'm fine with that. What if we mess with R23? So R23 is this top guy here. Curious about that. So if we go small, doesn't change a whole lot. If we go big, oh, wait a sec, wrong one. If we go big, now that to me seems like it's probably unstable. Yeah, I blew it up by changing the pot from 10K to 100K for bigger boosts. I'm not actually sure why it went off. Yeah, it's always tricky. So R23 definitely can make things go unstable. Let's try again with R23 and see kind of how far we can push it. And see if maybe we can get some clues as to if maybe the pole flipping has something to do with it. So let's see. First, let's boost. Now let's do something a little higher, so 10K, that's fine. 20K, still fine. 30K, still fine. 40K, okay. By the way, what if we go down? Okay. I don't know. 40K, 50K, still okay. What if we do 80K? Still all right so far. 100K, blow up. All right. So somewhere between 80K and 100K is our limit. Let's come back to that one, there's something I want to try with R23. So let me leave a comment to myself. Blows up between 80 and 100K. Okay, Ethan blew it up by changing the pot from 10K to 100K. Yeah, I'm not sure I wanted to make the potentiometer available to be able to be messed with. I think that's something I've got to decide with all the other circuits too. So far, I've been saying potentiometers stay stable, but maybe that's something that's worth taking a look at. So R24 is this feedback resistor. I'm going to guess we could also make it unstable if we push this one too far. Yep. Yeah. All right. So that one went unstable at 10K. Let's try it again here. So first, let's try going bigger. All right, that's fine. Doesn't do anything particularly worrisome. What if we go smaller? It's still fine. Still fine. All right, I'm guessing here. Yep. All right, so it blows up somewhere between 20K and 10K. All right, and now finally, let's try the capacitor. See if we can get something interesting out of that guy. All right. Cool. So we've got all the default values, and now let's try small capacitor. Yeah, that blows up. All right. Oh, bring it back here. Let's see. Is that okay? No, not okay. That's okay. All right. So, gosh. Whoops. Didn't mean to do that. All right, let's see. So there we go. All right. So let's try 1 nano. That's fine. Let's see. 100 pico. That's fine. Maybe 50 pico. Still fine. All right. Maybe 50 pico is a good lower limit. So I don't think we're getting anything interesting from that. Dude, 50. And maybe on the other side, 1 micro. Okay, yeah. So that kind of just pushes the cutoff frequency or the resonant frequency down pretty far. Maybe, yeah. You can take that as far as you want, I guess. Cool. Yeah, so the question, and I guess you could ask this about the capacitor as well, but the question for R23 and R24 is, does the instability happen because of this pole flipping? Right, so let's see. Actually, you know what I bet we could do? I bet we could just tame this cutoff frequency to we just clamp the cutoff frequency, and then I bet we wouldn't need the limit on the capacitor here. I don't know, maybe it's not worth it. But yeah, so what I'm curious about is, where do the poles live in where do the poles live when we change the resistors? So let's see here. Okay, yeah, I have an idea for how to do this. So what we're going to do is just copy this real quick and put that inside here. So R23 gets set, and then we set all these values. So we're saying that treble is at the max value. So we'll just say this is 1, and this is 0. So this is the max treble boost, is my understanding of it. We don't care about the B's, those are the zeros. We do care about the A's because those are the poles. And so we'll say root equals AS. So basically what we've got here is we've got this times S minus that equals 0, and that's our root. So the root is going to equal AS of 1 over AS 0. And there's a negative sign in there, if I'm remembering right. Yeah, okay. So we should be able to have a look at this now. So let's do this. We're not really supposed to do this because we're doing cout on the real-time thread, but this is just for a temporary test, so who cares? Unused variable K. Yeah, that's fine. Yeah, I guess we don't actually need this stuff in here. Fine by me. So yeah, let's see. Let's do this. So we've got this guy. Go back to all the default values. Have a look. Okay, I guess something got messed up in there somewhere. So let's restart. Okay, that's strange. Something went weird in there. Let's try that again. Double booster. Here we go. All right, cool. So we're fiddling with R23 right now, and we said this one blows up when we make it big. So let's bitwig plugin host. And so now we should be able to see what the actual roots are when we're setting this value. All right, there we go. We've got our debugger attached. So first, let's try the original value. Oh, well, that's gonna cause problems. I forgot the K. So let's see. Huh. For some reason, I can't actually see the A's. What's up with that? Huh, why won't it give me the A values? Whatever. Anyway, I don't really care because I got the wrong values in there anyway. We want the default, which is 4.7K. So let's see, R23 affects G3. G3 is that number. Yeah, that's kind of annoying that we can't actually see the A values here. Can I do it this way? Evaluating. Okay, so A sub S is 4 times 10 to the minus 41. So it's a really small number. That's A sub S 1. So that's the number here in this second spot here, right? Interesting that it's so small. I don't know. Also interesting that it's a positive number, right? There we go. All right, so basically we've got 3.9 times 10 to the 31 times S plus 4 times 10 to the minus 41 equals 0. So why? Oh no, so that's fine because this is the default value, so we know it works fine, right? So we end up with yeah, so we end up with a pole that is at well, that I can just do this, right? Evaluate root. Root is 7 times 10 to the minus 45. So it's a really small number, very close to 0 on the right side of the plane. So that's why we have to flip the poles to get that back on the left side. Kind of curious, though, why this gives us a positive number, right? Because it's negative G4. G4 is a positive number. G2 and G3 are both positive numbers. So how come when we get the negative there, we end up with a positive number? I don't know. That's a problem for another day. All right, so now let's try 80K, which apparently last time we tried it, that was stable. Oh, 80K. Here we go. So now our root is more or less the same, huh? Didn't seem like it changed much. Interesting. R23 is 80K. Yeah, okay. Seems like that's more or less the same. A little bit odd. These numbers don't seem to have changed either. Kind of interesting. All right, let's try going up to 90K, see what happens. So 90K for R23. G3 looks a little different. The A's still look more or less the same. And our root still looks the same. Interesting. And all right, now we're going to do 100K, which from what we saw last time should blow it up. So there we go. That's 100K. G3 is a little bit different. Our A's seem to be the same. Interesting. And our root seems to be the same as well. That's something tells me that can't be right. But what am I doing wrong if that's the case? Maybe I flipped around my 0 and 1 here. I don't know. Let's go into the actual coefficient calculations and see what we get out of that. So first of all, what is Kerr treble? Kerr treble is 1. That's what we did too. So that can't have been the problem. AS is different numbers. Okay, so something's wrong with our other way of looking at things, but whatever. In here, we've got something that is seemingly correct, so that's good. Still makes me a little bit curious, though. Should look into that again. So that's our A values. So when basically we've got that times x minus that equals 0. So let's do a little Wolfram alpha here. If I can maneuver my screens around well enough. Yikes. Wolfram alpha. Okay. So we've got that number times x plus that number equals 0. Right. And that's going to be a negative number, is my understanding. Yeah. Well, I guess we actually have two roots, right? So where's the second root? Oh no, okay, we only have the one root. Yeah, that makes sense. So we've got this root, and clearly that's on the left side of the plane, which is stable, which means we shouldn't be flipping our roots, which we were doing before. So let me try this. Let's go back to, yeah, I know it's gonna, okay, this is just gonna scream at me until I fix it. So let's just go back here and get out of the way. Deactivate, reactivate. See if we can get something real out of this thing again. All right, so when this is 4.7K, what is our pole? So this is at like the standard resistor value for R23. We want to figure out where is our pole when we're there. So these are the A values that we've got at that point in time, and see how this 0 value is a positive number. I think that's the main difference we're going to see here. So if I swap these numbers out, we'll see yeah, so now we're seeing that our pole is on the right side of the plane. It's a positive number, and that's why we needed to flip our poles. So let's do this. The way that we solve for this is we say that x, so I think we had this right here, it just didn't show up in the debugger for some unknown reason. Also, let's just get out of this for now. Yeah, so let's try this. So we're going to say, let me make these const, because why not? We're going to say that the root should be that, right? Because the way that we would solve for the root is we subtract that value over to the right side and then divide by that value, and that would give us the root. So here we'll do if root is greater than 0, then we want this, else we want to do that. So actually, let's do this. If the root is greater than 0, we'll just put everything inside that if statement. And if it's not greater than 0, then we just don't need to do the flip, and things actually become a little simpler for us. We can just use B, U, and AU. I think the U is supposed to stand for unstable, but now in this branch of the if statement, it is stable, which is cool. So if the root is greater than 0, we need to flip the poles. Otherwise, we don't need to. And I think this should allow us to get away with much larger ranges for our R23 and R24 here. Let's see what we get. That's very interesting. Yeah, this is an interesting circuit. I was talking about this with someone a few months ago. I forget who it was. Maybe it was almost a year ago now. Wow, that was a long time ago. But it feels like it was just the other day. But we were talking about this exact circuit. And it's super weird because if you just do nodal analysis directly, you end up with an unstable circuit because you have this pole that's in the positive part of the plane. And so if you flip the pole, then you get the right frequency response, and you can get a linear filter that does what you want it to do. But yeah, it's curious then, okay, so why does that work in the analog circuit if that's the case? And so, yeah, I don't know, maybe there's some op-amp clipping and some other stuff that's going on that's, just part of the sound of the circuit at that point. But yeah, it's definitely a curious thing. So here's our 80K. Let's try 90K. Nothing changes. 100K. All right, we haven't gone unstable yet. Let's just crank it up all the way. Cool, yeah, so that seems fine. And yeah, let's see also, I'm just curious, when we hit our different branches. So right now we should be in the flipping the poles branch. And then once I bring R23 up high enough, we should get to the no flipping branch. So here we're still not flipping the poles. Here we still are flipping the poles. Here we're not flipping the poles anymore. There we go. Cool. Neat. Yeah, that's pretty cool. I guess flipping the pole, there's only one pole. Yeah, and then if we bring that back there or bring that way up, and it's still flipping the poles, and now we're back into that first branch. And then let's see what kind of damage we can do with R24 now that we have kind of fixed that instability with R23. So this was 100K, and previously we could make it go unstable by bringing it down to something like 20K or 10K. So let's see, R24, if we bring it down to 30K, we're there. If we bring it down to 20K, we're there. So we're still flipping the poles. We bring it down one more time. Now we're not flipping the poles. Interesting. And let's see if we go unstable. We do not. All right. Good news. And let's go even smaller. Cool. Yeah. So I may put the limit at 1K just because below 1K it gets so quiet that maybe you wouldn't want to hear it anymore. I don't know. I'll just leave it. Why not? People want it quiet, they can get it quiet. And then if we go back up, now we're back in this branch of the if statement, and all is well. Cool, yeah. So there we go. Now we've got a netlist view for the treble booster, except we have the wrong circuit schematic. So let's go and do that real quick. It won't be too bad. And yeah, so we can now get around our treble booster circuit without having blowups. So that's a neat thing to be able to do. All right, yeah. So I'm just gonna pop this circuit in a schematic real quick, or create a new schematic for it. But yeah, if folks have questions or anything while I'm doing that, I'm happy to talk about whatever. This is treble booster. So we've got, well, Uh-oh, my computer's not happy. Okay. All right, so we need a branch going up, so I'll leave a little space for that. Oops. R21 and R22. Cool. Let's get our op amp going. Oops, wrong way. There we go. All right, so this is a inverting op amp. Yeah. Right. Thanks, Ethan. Yeah, thanks for helping out too, remembering the order of the resistors, because I had completely forgotten that and had neglected to write it down. I'll figure out a way to write it down tonight so that I don't forget it again. Actually, I think we can just use this comment here as a way of remembering. So this is R22. Whoops. We want to leave the comment. We want to get rid of the question marks. There we go. Cool. Okay, I want another branch here. I don't know if I left enough room for myself. Yeah, okay, that'll be fine. And then let's see, we want a potentiometer. Maybe let's shrink that guy a little and put the pot in here. And capacitor, I didn't leave myself enough room, I don't think. Yeah, that's not enough room. Okay. Let's see. Oops. Well, I'll just here. Yeah, so I guess technically that's not really ground, but it's a virtual ground. So for the purposes of this circuit, we'll say that it is. So that's C14. This is our treble. I labeled C14 correctly, yeah. All right, and then we've got our 100K R24 coming around. And then we've got another resistor above that. We're coming across everything here, and that's our 23, right? Yeah. Oops. Cool, and now we can wire it all up. Wires, boom, all right. And then should I add a level resistor? Sure, why not? It's like, again, it's kind of like a virtual thing that either is or isn't there, depending on how you want to think about it. Awesome. Cool, that's a simple enough circuit. Let's get that in the plugin. Cool. Yeah, so we should be able to build it now and see the actual circuit schematic, which is going to take a minute because it's a full build because I had to change around the binary data. I've actually been thinking about moving away from binary data for BYOD just because there's so much of it. But I don't know, I haven't decided yet. Maybe, maybe not. If anyone's curious, this is the system I've been using now instead of binary data. It has its own kind of pros and cons. I'm not saying that it's perfect, but there are some things that I like a little better than binary data about how it handles things. Let's get rid of that copy. But yeah, so this is a CMake resource compiler. So basically what you do is you say add resource library, and then you can give it a alias for CMake. You can give it a namespace that it will use in your C++ code. And then you can just link it to your C++ library or executable or whatever. Then in your C++ code, you include their header and you declare your, basically your file system. So you just say, hey, this is a file system called foo. And I defined it in my CMake here. And yeah, it's pretty neat because you can do a whole bunch of stuff with basically having a virtual file system that exists both on your computer and in your CMRC library. So you can do get file system, open files, and whatnot. And yeah, I found that the compile times are usually a little bit better than with binary data as well, especially when you have a lot of it. But yeah, I don't know. I haven't fully decided if it's worth the effort to move BYOD over to that system. Maybe not. I don't know. All right, what's our problem here? Treble booster schematic. I forgot to give the correct name. All right. Yeah, so there we go. Some fun circuit modeling stuff today. I'll probably, I might do another one next week. We'll see. If not, definitely the week after. But yeah, it would probably be some BYOD stuff. I don't know, maybe something else. We'll see if anyone has requests. I'm happy to take requests. But yeah, we'll see. I haven't decided yet. Thanks, Ethan. Yeah, thanks for tuning in and pitching in with all your thoughts. Definitely good to have a active participant. All right, let's try it. Awesome, there we go. Yep, there's our schematic that we expected. Still got all of our component values, R23, R24, C14, no RL because it's virtual, and virtual ground. All right, there we go. Cool. Well, yeah, thanks again, everyone. And yeah, I'll be back in a future video, maybe next week or maybe sometime after that. All righty. Thanks, everyone.